to doing that, we can Research Institute with 200 million euros of annual funding. We are a major player in Finland. More than 1/3 of our Finnish innovations involve some of our expertise, and we employ more than 2,000 people. At the same time, we operate in an increasingly international field, with almost a half of our turnover coming from abroad. So what is then the motivation behind of sustainability in electronics and optics, and especially flexible electronics? So if we think about globally, the electronic waste is increasing rapidly with 6.5 compound annual growth rate, and currently only 20% of that is recycled properly. So that means that the valuable components and materials end up in environment, and many of these can be even toxic. This forces electronics industry to guarantee that they are not running out of some rare and valuable materials, and to seek for alternative materials based on the safe and renewable resources. And at the same time, ways to recycle of non-renewable materials from electronic waste are needed to consider as well. And when we think at the same time, the global consumption of material resources is expected to be more than double between 2015 and 2050. So this shows that these challenges need to be addressed. So what are then the drivers and actually the tools for this sustainable electronics? So there are already several global and European sustainability actions ongoing, like such a European Green Deal, and of course United Nations sustainability goals. That was also electronics industry to think how to decrease environmental impact of their products. At the same time, there is continuous need for more functional properties and improved performance. And all the time, the end-of-life options and these needs to be considered really carefully. So we need to more eco-design, more circular design and thinking, and understand that we need to maintain the value of the products. But at the same time, there is also particular industrial needs that new type of electronic solutions that are emerging are at some point of their life cycle end up to the biological environment, either in purpose or accidentally. An example of these kind of products are sensors for intelligent packaging, environmental monitoring, disposable diagnostics, and precision agriculture. And there we need also solutions which are from renewable resources and can biodegrade in environment, or in some cases compostable. At VTT we have made an estimation that if we use for our lignocellulosic materials, which are nowadays used mainly about pulp, paper and board applications, that if we increase the value of these products, we can actually achieve significant export improvement. We can do this together and also setting common goals and actions, and this needs also investments. But it's possible at the same time mitigate to the climate change, and value of the production can be increased. And one of these kind of emerging application areas is also electronics. So today I will show you some research topics towards what we have done at VTT about in this area of sustainable, flexible and optics, flexible electronics. and optics. So those cases are sustainable energy applications, renewable bio-based overmolded structural materials, case of functional components, which we have utilized in distinguishing material properties, and optical cellulose-based materials. Firstly, I would like to go through you about what are then the opportunities of this kind of sustainable materials. There is of course a lot of different type of biopolymers in the field. If we think about conventional materials which are fossil-based and recyclable, then we are in this left corner. But more and more we would like to move to this upper right corner, where these materials can actually be even at the same time at least recyclable and bio-based, but also compostable, and also they might have also biodegradation properties. And those kind of materials can be bio-based polymers, regenerated cellulose, and nanocellulose options. Then I would like to discuss with you about the batteries. Batteries are one of the key elements to enable the use of sustainable and clean energy. We need them in electric vehicles to reduce the carbon dioxide emissions of transport, and also in wind and solar parks to store energy from renewable sources. And all the power to portable electronics we carry around each day in our lives. In order to make this clean energy transition happen without causing other environmental and societal damages, batteries need to become more environmental friendly and sustainable throughout the whole value chain. And batteries are really the component where many of different type of new chemistries can be addressed. The first step towards lower environmental impact would be the more abundant materials using, like just a natrium and other biomass nutrients. The second step would be more towards solid-state batteries with organic materials that are safer than lithium-ion batteries that have toxic or flammable liquid electrolytes. And finally, the batteries could be made compostable by using cellulose or biopolymers as a substrate, as a casing, as a binders, and separator materials as well. In ongoing our flagship program, which is scientific cluster in biomaterials in Finland, Essers, with collaboration with Aalto University, we are actually studying the biochars and how the biochars can be one really valuable component in energy harvesting and storage applications. In this project, we have done hydrothermal carbonization, and we have concluded that we can replace fossil-based coal in some particular applications, which are like solar cells, supercapacitors, and maybe even batteries. And in this project, we actually use really low-cost biomasses like side stream type of biomass fraction. Then one demonstration examples of these kind of structural electronics which are all well molded. So in this bioboat, we actually made a sensor for clean indoor air quality, and in this demo boat, lights turn from green to red with increasing CO2 levels, and then there is potential to make movements to the indoor ventilation if the crowded space is too much. In this demo case, we used many different type of materials, but we made also comparison about the properties in both actually films and overmolded structures with fossil PAT and biopolymer, actually in this case a cellulose derivative. And both cases we noticed that we actually can improve electrical properties, so resistance reduced as to half and at the same time processing temperature lowered. And that is actually one key actor behind that is the adhesion between silver and substrate. So with improved contact between those, it's possible to achieve these excellent properties. Then there has been ongoing this kind of EU project, pilot project in paper, and there the aim has been make this kind of smart printed electronics based on the multifunctionalized paper and also based on the nanocellulose films. There we can actually, there has been actually done modifications for the films to provide decent conductivity, water repellence, barrier properties, and other tailored porosity, for example. And with that kind of concepts, there has been demonstrated batteries, different kind of displays, antenna, and sensors. And then those all has connected and fabricated to the common platform and derived use cases. Then one example about the optical cellulose materials. So in this case, we utilize this kind of multi-structural new type of fiber. So in there is the core is the regenerated cellulose, and as a shell we use cellulose acetate. And based on the different properties of those materials, it's possible to achieve this kind of optical cellulose fiber, which can be used, for example, water sensor applications. So, as to conclude, the resource sufficiency is a global challenge concerning all businesses, but also electronics, photonics, and diagnostic industries. And that's fortunate that there is ways to tackle this challenge with different sustainable approaches. These sustainable approaches also include green, recyclable, and biodegradable and materials which are done from renewable resources. And companies could take actually this sustainability as their competitive edge and offer products with similar or even better performance than non-sustainable competitors. But however, we can expect that the full-scale exploitation of renewable materials only after the materials' properties and performance as well as their process compatibility have been tailored for needs for these industries. So there is still a lot of research challenges to work with, but we truly believe that even beyond the renewable, functional and active bio-based materials provide future solutions. So I would like to thank you for your attention, and I would like to conclude my presentation to that we did this multidisciplinary experts working group. Together we are searching greener tomorrow and making a lot of efforts and work to make that happen. Thank you for your attention.
Dear ladies and gentlemen, it's my pleasure to have the opportunity to report on some investigation we have done for the resolution of global challenges in cellulose man-made fiber production. My name is Meister and I'm from the TITK Torvinen Institute for Textile and Plastic Research, which is situated in the so-called Green Heart of Germany in the Free State of Thuringia. In the images you see the main building of our hometown, the Castle Heidecksburg, as well as the main building of our institute and the TITK's institute's area. TITK is a modern research institute for the manufacturing of functional and constructional plastics. Its core competences are native polymers, which are mainly used for solution spinning to manufacture cellulose man-made fibers. reinforced composites for weight light application, synthetic polymers which are used for functional compounds, especially in medical application, and functional polymer systems which are based on polymers with special electrical and optical properties. The global trends and challenges in our time are characterized by a global population growth. So 8 billion people were expected in 2020. There is a global increase of the gross domestic products. The compound annual growth rate between 2011 and 2020 was 2.4% per year. The climate changes, the marine microplastics pollution, and the customers' demand for sustainable and safer products. As a result of this situation, a strong increase of man-made fiber demand worldwide was seen, especially in countries like China, India, Indonesia, or Vietnam. The actual consumption level will catch in 2020 the level of per capita of Western Europe at about 25 kg. There's a stagnation of cotton production at about 28 million tons per year because of the strong request of arable land for food cultivation and of reduced consumption of water and herbicides. And there is also a high cellulose man-made fiber demand because of their outstanding moisture management properties above average. From these results, a cellulose gap arises at the end of 2020 in the range of about 5.3 million tons per year. The reason for that is the doubling compound annual growth rate of cellulose man-made fibers in the last decade. So it is expected a cellulose gap at 2020 of about 5 million metric tons, at the end of this decade of about 10 million metric tons, and in 2050 of about 50 million metric tons. That brings the requirement that man-made fiber production of today, which is characterized by a linear economy, has to be changed tomorrow to a circular economy. Especially in cellulose man-made fiber production, new raw materials or raw materials mixtures like paper, agricultural residues, or recycling pulps make it possible that circular textile economy will change, and that could be offered broader approaches for resolution of improved demand situation. Let me please give some examples how to overcome this situation by the manufacturing of dissolving pulps from paper pulps. Several technological approaches were developed were biorefinery processes for the production of dissolving pulps, and side products like lignins or sugar-based products are possible. Or even alkaline pulping processes where high cellulose yield was possible with very narrow distributed cellulose pulps, but with a bad dissolution property. You see its image slow after the dissolution starts, a strong ballooning of these fibers, which ends up with a very bad dissolution state. Or by adjustable solvent systems on the basis of ionic liquid and sufficient co-solvents, where hemi-rich kraft pulps are treated for separation of pure hemis and pure dissolving pulps. This process is possible for all hemicellulose types, and it is a simple transfer from paper pulp to dissolving pulp with a quality even for cellulose acetate manufacture. TIDK has investigated a special enzymatic treatment of paper pulp. The results are seen in the table. You see in column 1 the results for a paper pulp which was not enzymatically treated. You see the high degree of polymerization and low values for zero shear viscosity, which stands for a very poor dissolution behavior in the lyocell process. That means in dissolution in N-methyl morpholine N-oxide. If you treated the pulp with different mixtures of endo and exoglucanases enzymatically, you end up with lower degree of polymerization and higher zero shear viscosities. That means with a better dissolution behavior. That brings us to very stable spinning runs and fibers which have good mechanical properties. You see increased tenacity, elongation, and also loop tenacity. Another opportunity could be to make pulps, dissolving pulps of annual plants. For that purpose, the whole new value-added chain had to be created. Actual in transfer is our own lyo-hemp process, where we started from the hemp cultivation and pre-treatment to come to a hemp tow, which is a raw material for the pulp cooking. The resulting pulp could be used for dissolving and fiber manufacturing up to semi-technical scales. And also we have investigated the yarn manufacturing and the production of fabrics. For that purpose, plant bast fibers has to be processed in a two-step technology, and this technology was developed together with the company OP Papierna at Olsztyn in Czech Republic. This company is member of the Delford Group, Austria. In the first step, the soda cooking process, the organic impurities could be separated from the pulp. For that purpose, caustic soda consumption in the range of 25% per amount of agro pulp was required to come to acceptable Kappa numbers. In the second step, an acidic bleaching sequence for adjustment of the degree of polymerization and the separation of inorganic impurities was required. You see in the table on the right upper side that we end up with acceptable dP of polymerization, high alpha cellulose content, and low concentration of heavy metal, alkali and earth alkali ions. Last but not least, dissolving pulps made by chemical fiber recycling of fabrics. The process of choice, especially for the typical mixed fabrics, which are also known as polycotton, includes thermochemical treatment of fiber-forming polymers. You can contain either a depolymerization into monomers or a dissolution in suitable solvents at maintaining of the polymeric or oligomeric fiber character. Hydrothermal processing, that means the depolymerization by means of steam, temperature, pressure and catalysts, is typical for this chemical recycling process. Important to stamp is that monomer purity at depolymerization procedures strongly depends on additives which are applied, while all former processes like polymerization, textile processing, customers use and so on, and these impurities had to be separated before or while chemical recycling. We also investigated all this pulp in dry wet spinning at lyocell to manufacture lyocell fibers, which are available at TATK Group. This is a typical process, and you see the main important is that when excess water is evaporated, a dissolution is very fast. And in this dissolved state, cellulose could be formed into fibers and products very easily. This is a spinning trial scheme with the dough preparation, the spinning over an air gap, the washing and the solvent recovery steps. There are images of these different skulls we have available at TITK. That brings us to the conclusion. The global challenges regarding growing number of world population, gross domestic products in selected Asian countries, climate changes and dramatically intensified pollution by marine microscopic plastics will change the whole textile industry. The world man-made fiber demand will increase in the next decade by more than 4% per annum. Because of the stagnation of cotton cultivation, cellulose man-made fiber will increase disproportionately high compared to all other fiber types by more than 6%. A cellulose gap of about 5 to 10 million metric tons is expected at the end of current decade. A change from a linear into a circular textile economy could help to overcome the global challenges and to safeguard the needs for sufficient dissolving pulps. Paper and plant-based pulps originate from agricultural residues could be easily converted into high-purity dissolving pulps. But the major amount of required dissolving pulps could be safeguarded by chemical recycling of pre- or post-consumer textile wastes. Mainly the lyocell technology will be able to spin again high-tenacity fibers from those pulps. Thank you very much for your kind attention. Please ask questions or give me your comments. You can see the contact at the upper side.
First of all, I would like to thank EPNOE, especially Peter Verdien and Carmen Freire, for giving me and the Institute the opportunity to present today at this conference. The title of my presentation is called Superheated Steam Treatment of Wheat Bran. The content of the presentation is about the outcome of a study which was done in conjunction with our industrial partner Kellogg's, in which we investigated the potential of superheated steam as a novel modification tool for wheat bran in order to make it more accessible and more functional for food application. But prior to this, I would like to explain something about my own institute. In a nutshell, WFBR stands for Wageningen Food and Bio-Based Research. Is part of the Wageningen University and Research structure. WFBR has its own expertise on carbohydrates called biopolymer modification, and this group is specialized in the development of novel processes for modification of pectin, starches, cellulose, but also other biopolymers as proteins and lignin. In this group, I'm active as a project leader and senior scientist, and the core of my own research is about development of clean label modifications of starches, novel dietary fiber, gelatin replacement, but also development of novel starch-based adhesives. Now, turning back to the content of the presentation, superheated steam in general. What is superheated steam? Well, steam basically can be divided into three categories. You have wet steam, which refers to mist or fog. You have saturated steam, which the vapor phase and the liquid phase are in equilibrium, and you have also superheated steam. And superheated steam is heated above its condensation temperature. Hence, no condensation can occur anymore, and it's visualized in the picture on the right. Hence, superheated steam is also referred to as dry steam. Now the question is, what does superheated steam make special? Superheated steam is characterized by the fact that it has a higher heat transfer in comparison to hot air. And that's due to the fact that water molecules are present in the steam. And the water activity plays a very important role in this field. So you can enhance this the capacity of the heat transfer by adjusting the water activity, which can also be stirred or controlled by the temperature and the pressure. And this can be very beneficial in oven systems for certain bakery and frying applications. But recent over the past couple of years, by our own institute pointed also out that superheated steam can be very beneficial for delignification of liquid cellulose or to make biomass more accessible for further treatment. For example, for fermentation into bioethanol. Now, talking about wheat bran is also a kind of biomass. And the bran is the outer layer of the wheat kernel and removed during milling. And in older days, it was considered as a side product with less value and only suitable for feed. But as it consists out of the pericarp and the aleurone, it turns out that it's very rich on nutrients, vitamins, soluble and insoluble fiber, antioxidants. And this is all connected. All these components are connected in a very dense and complex network, which is displayed in the picture on the right. Now, as we are aware that wheat bran is very rich in nutrients, it gained interest for food applications. And nowadays it's added more and more in certain bread applications in order to enrich the dietary fiber level. Still, we are aware of the fact that wheat bran doesn't contribute to functionality, as it hardly interacts with the other ingredients within the formulation matrix. On the other hand, we are also aware that the release of the nutritional components during digestion is not always very efficient. And that's due to the very dense and complex matrix. So when we could improve either or functionality as well the release of the nutritional components, that would be very beneficial and enhance the usage of wheat bran in various applications. Now, as we turn back to superheated steam now, superheated steam turned out to be very beneficial for treatment of biomass. Then the question arises if this also can be an interesting tool for treatment of wheat bran and making wheat bran more accessible and more functional. Then the question arises, what type of conditions do we need to use? So we started with a design of experiments. We varied the temperature, ranging from 120 to 160 degrees Celsius, the water activity from 0.5 to 0.7, and of course the residence time. Immediately it was observed that darkening or browning of the samples occurred during SHS treatment, and already indicates that structural changes within the wheat bran matrix have occurred. So we got very curious if morphological changes could be observed by use of microscopy. And by use of UV microscopy, we could observe that loosening of the cell wall structure was induced, and that also affected the increase of the water binding capacity. The loosening of the cell wall structure is most likely due or an indication for a break in the tethering polysaccharides, because these cause disentanglement of the cell wall structure. Further analysis were carried out by suspending the wheat bran or the SHS treated wheat bran in water. And we immediately can see that the control in comparison to the samples that were treated with SHS, the control is more dense, and that the water binding capacity of the wheat bran, the insoluble material, is higher than the control. In average, it's about 35% increase of the water binding capacity. So the loosening of the cell wall structure results in a higher water binding capacity. But then the question also emerges, did it also affect solubilization of certain components of the wheat bran structure? So we started to investigate also the supernatants. And we isolated the components that were present in the supernatants. And what we observed is that in function of temperature, but also in function of the water activity, the amount of soluble material increased. Then we became interesting to find out the composition of this material. After destarching of the samples, we made a sugar analysis of its composition, and it pointed out that most of the material that's released via SHS that consists out of arabinoxylates. Well, we also observed a decrease of the galactose percentage, but that can be explained because these are part of the arabinogalactone proteins, the Ig proteins, and these likely will not get solubilized during SHS. So as the release of the other components increases, it explains why the percentage of galactose decreases. The extracted fraction was also analyzed by GPC moles in order to get insight in the molecular weight distribution. And what we observe is similar as we have seen with the other analysis, an increase of the water-soluble components in function of temperature. But we see also that the treatment at higher temperatures reveal a bimodal distribution. And when we turn to the next graph on the right, we see that the cumulative weight fraction of the extracted samples, or in molecular weight, higher than the control, with exception of the condition that was applied at 160 degrees Celsius and a water activity of 0.5. And the reduction in molecular weight in this condition, but also the bimodal distribution, points out to degradation, because when we apply the same conditions but at a higher water activity, that bimodal distribution disappears and the molecular weight stabilizes at a level higher than the release arabinoxylane of the control. So what we learn is that by stirring the water activity, we can avoid degradation. We also did some additional analysis on supernatants regarding the formation of color components via UV absorbance spectra. And we saw a small increase at a wavelength of 280 nanometers and 345 nanometers, which point out to caramelization and to Maillard reactions. So altogether, summarized, we can say that SS affects the structure of the wheat bran. Loosening of the cell wall structure causes an increase of the water binding capacity, a higher solubilization of high molecular arabinoxylates, which depends on temperature, but also on the water activity, and that we should avoid higher temperatures in combination with low water activities in order to prevent degradation. Now we come to the second part of the investigation, which is the application of the SHS treated wheat bran samples. Colleagues in my department or in my institute that are specialized in bakery applications have performed these studies. They choose cracker formulations to investigate potential improvement by use of SHS treated wheat bran. What I will do in this presentation is not to go in detail about these studies because it requires a second presentation, but to tell you in a nutshell about the outcome. What we have seen is that SHS treated wheat bran samples improve flavor, and especially the conditions that have been applied between 120 and 140 degrees Celsius. But concerning all other properties, functional properties of crackers, it remains unclear whether we claim an improvement or not. We saw that differences among samples occurred when we applied higher moisture levels in our formulation, but we have not too much evidence to say, well, there is a clear improvement which is induced by SHS. Now we come to the third part of the investigation, the digestibility studies. As we have seen that most of the components that are released are arabinoxylates. And as they cannot be digested in the small intestine, we were interested to see what would happen in the colon, and especially the fermentation in the colon by the bifidobacteria. And the way these analyses proceed, and that was done, these analyses were done by all colleagues of mine from TNO. You take bacteria from human stool, you isolate these bacteria, then you add your components in which you want to analyze to these bacteria. Then you cultivate the system for a certain amount of time and at a certain temperature. Then afterwards you extract the bacteria. You identify them and you quantify them. And what we have done, we took the extractables, the arabinoxylates that were released due to SHS, and compare those with other prebiotics such as fructooligosaccharides and galactooligosaccharides. And what turns out that the performance of the released arabinoxylates by SHS have a similar performance as bifidogenic agent as galactooligosaccharides and fructooligosaccharides. And from that point of view, we may conclude that SHS treatment of wheat bran releases more soluble prebiotic material such as arabinoxylates. And from that point of view, SHS treated wheat bran could act as a kind of release agent for these types of biopolymers. So altogether, the main conclusions of this investigation are that SHS affects the structure and the morphology of wheat bran, it loosens the cell wall structure, it increases the binding capacity, it increases solubility of high molecular arabinoxylates. These have similar bifidogenic properties as GOS and FOS. From that point of view, we may conclude that SHS could act as this kind of release system for these types of polysaccharides. When we apply optimum conditions, then we would choose for between 120 and 160 degrees Celsius, but using higher water activities in order to prevent degradation. Furthermore, applied in bakery applications, then basically until now we can observe that it enhances flavor characteristics. I would like to thank everybody who contributed to this project. In case you have questions or you want to know more about the research, then don't hesitate to contact me or other colleagues. And now it's time to raise questions. I'm looking very much forward to answer your questions, and thank you very much for your attention.
Okay. Good afternoon to all.
Thank you.
First of all, I would like to compliment the speakers of this session, acknowledge their participation, their collaboration for the success of this EPNOE event in the Tecnicelpa. Before going into the question and discussion of these talks, I'd like also to acknowledge the organization of Tecnicelpa and CADC for this opportunity of EPNOE organize this session. And also congratulate the organization for this very interesting conference, well set up, particularly considering a totally different format that we are used to. Before going to the question, I would like just to say some words about EPNOE. This session is a EPNOE Connect event co-organized by EPNOE and Tecnicelpa CADC. And for those that do not know EPNOE, I just want to say some words. EPNOE is the European Polysaccharides Network of Excellence, is the non-profit association that intends to connect all the international community that works with polysaccharides. That is to say, that works in fields where polysaccharides have an important role. And the focus of EPNOE is centered on research, innovation, and education. Presently, we have 43 members from 16 countries in Europe, including 35 universities and research organizations, institutions, and also 8 companies. And the main activities of EPNOE are related with research and industry events. We promote the organization of events, of network events between research and industry to prepare project proposals. We also act as a source of expert technical knowledge for industry, but also for the civil society. And another important activity of EPNOE is the organization of conferences and workshops. We have 2 conferences, one dedicated for young researchers, the EPNOE Juniors Conference, and a large conference, and these 2 conferences alternate each other and are biannual events. This year, in 2021, we will have the large EPNOE conference that will be in Nantes. Presently, we have the after submissions open until the end of March, and I think that most participants of Tecnicelpa could participate in EPNOE conference because lignocellulosic biomass is mainly composed of cellulose and hemicellulose, important polysaccharides, and certainly you will find this for also an important event for dissemination of your work. And now I would like to go into the discussion of these talks. We have several questions. I hope we have time to discuss all of them here in our forum. I think we can do it using the same order as the presentations. So we will start with Katariina. Here are several questions. The first one is about there are already market-ready products with flexible electronics or optics based on cellulose or other polysaccharides? If so, can you give some examples?
Hello, hopefully you will hear me.
Yes.
So thanks for the question. So I think we are quite ready on the stepping to the markets with those solutions. Like I mentioned, we have this European level in-paper products, which is actually ending in this year, and then we have actually also in Finland this kind of consortia together with companies that we are seeking these different kind of end applications. So basically, I think there is the question is that there is already materials which are available in at least in some extent in the markets. Those can be at least be passive substrates. They might be also can be utilized in structural electronics already, but we still need this kind of more co-creation together with companies that we really find those required properties and mission is that they will have also the active role in those materials, not only passive. So there is applications like already in the flexible printed electronics that are nearby to being in the markets, and also I think in energy storage. But in optics, I think that we are a little bit not so in that way so near in the markets yet. So it's more in the scientific level yet.
Thank you very much. We have another question for Katariina. What are the future applications of cellulose-based optical fibers? Can it replace optical glass fibers?
So first of all, I think we are now actually seeking, and we are already we have publication together with all the universities, actually quite near one. So there we have found this kind of crystal band structure in cellulose, and that enables the future optical solutions. Then what those might be, we have been figuring out that at least in short distances we can utilize these kind of optical fibers. So for example in biomedical applications, because they have this biocompatibility, they are, I think, really interesting ones. Then we have already seen that in constructions, maybe detecting the moisture, that can be one solution. So maybe these kind of solutions where you can where is need for the not too big distances. So in those I see, but cannot say for sure that can those replace as a glass fibers, but might be.
Okay, thank you. I also have a question related with the water sensitivity of cellulose-based materials. How this could be a problem for electronics and how it could be overcome.
So yes, you are absolutely right that cellulosic materials are hygroscopic. So we can actually take also benefit for that, and we are actually utilizing that also already in quite many applications, and we have also done a lot of extent research about modifications, chemical modification of cellulose, so that they can be hydrophobic as well.
Okay, thank you so much, Katariina, for your talk and for all these clarifications and comments about this subject of research. Thank you so much. And now we will move to the talk of Frank. We have also here some question. What is the future of viscose fibers considering the demand of man-made fibers you mentioned?
Man-made fibers, especially based on cellulose, it is the segment inside cellulose man-mades, the man-made fiber, which is strongest growing this time. The reason for that are the good values for sustainability, product safe, and also not only the products, also the technology which is used for the manufacturing of cellulose man-mades is the best we have available. And of course, all fibers based on cellulose, that means viscose or modal or even lyocell, are biodegradable. That means we have no contribution to this dramatic increase of this marine microplastics, and that are advantages for all fibers which are in the interest of environment and customers.
Thank you. The other question is related with the dissolution of cellulose and is about why the solution via ballooning is bad. Does it mean that fiber dissolution via unwinding mechanism is better?
The reason for that is ballooning itself is not bad. Ballooning, but as the end of this dissolution, that is a bad situation. That means we have at any time in solution spinning this behavior of polymers that you find inside the dissolution process is ballooning, and it is not only typical for cellulose, it's also typical for synthetic polymers.
Okay, thank you. I also have a question related with the comment that you refer about that one strategy is to use other raw materials rather than, for example, cotton, for example, using residues, agroforest or lignocellulosic residues. My question is, cotton is a high pure cellulose material, but these residues have other components and we need to cook them or to delinify the biomass to obtain cellulose. And these processes are not very sustainable, at least the most conventional ones. You know that in the later years, we had several progress in these fields. How the impact of this process compare with, for example, the production of cotton when we consider sustainability?
Yes, I understand what you are meaning, but you have not to forget that the growth of cotton is a problem, not cotton itself, and also the application of cotton. But you have to use very good arable land for that cultivation, and you need a lot of water and fertilizers. And that is a problem because there is a competition together with the same land for the cultivation of food. And if there are more and more people on the earth, you need this arable land for the cultivation of food and not for cotton. And that is the reason why the cotton cultivation stagnate.
Okay, but the forest also needs land. The fact here that you are suggesting residues, right, that are produced from other activities, right?
Other kind of land, where you have woods, where you have hemp cultivation, you have no opportunity to grow cotton. And that is different.
Okay, thank you so much, Frank, for
Welcome.
your talk. Very interesting, and also for all this interesting discussion. And now for Maurice, we have also here some questions from the audience.
Thank you.
And the first one is, what about degradation products formed in SHS processes?
Well, I can give an answer to that. Of course, wheat bran is a very complex material. As we already saw, browning can occur, and that's most due to caramelization or Maillard reactions. We also checked up on 5-HMF, and the funny part is we hardly see 5-HMF forming. And that's very interesting because it also plays an asset in the SHS treatment of other lignocellulosic material, especially for bioethanol. SHS turns out not to induce much 5-HMF, and that's an advantage for these types of technologies. Furthermore, what we saw is that you get degradation of your soluble extracts, and that's of course just hydrolysis. We don't see that changes in the polymer itself occurred. So, summarize, I would say, when you talk about formation of side components, we hardly see 5-HMF, although caramelization and a Maillard reaction were visible.
Okay, thank you.
Yeah,
Just a brief question about the application of this methodology to the to the fractionation of biomass, of lignocellulosic biomass. You thought that this can also be applied to this field, but it is applied only the steam or also other chemics to promote the delignification?
Yeah, of course, when you talk about other lignocellulosic materials, you will also add some acid. You have to add because this is something you cannot do with wheat bran because the purpose was to use it for food. But of course, when it is about the delignification, certainly when you go into bioethanol, then of course you need to have an acid catalyst or another catalyst additional, and for the whole disentanglement of the matrix. But for food application, we did it without any kind of catalyst. But you're right about that. Solely using SHS on, for example, pulp or for wheat straw, of course, it affects certain aspects, but it doesn't. You need a catalyst in order to enhance the further disentanglement or the dissolvement of the material. That's for sure.
Thank you. Thank you. Are already at our time, but we have here a general question, and I think we can just finish with this question. It's a general question about what are the biggest challenges associated with the production of sugars from biomass at an industrial scale. So I leave it free for your answer. Anyone can please comment.
The biggest challenges in that field. Well, of course, I have some other colleagues that are specialized, especially in that field. But what I always observed, of course, you have the first generation, the second generation, that difference, whether you use starch or biomass. Then, of course, when you come to the conversion of starch, is of course very efficient, but you take starch away from food. That's a disadvantage. When you talk about the conversion of bioethanol into sugar or sugar derivatives, yeah, of course, I think that you have, of course, in the biomass more components, and you need to validate those as well in order to make it a commercial process. So you cannot just solely look to the one component releasing out of that. Then you need to also look to the lignin fraction and the other fractions.
Yeah, maybe one addition to my behalf on that. So I'm not the expert in the sugars field, but I think also I agree. So that I think it's about to cascade use of the biomass, and also I think there might be some challenges about the unevenness of the biomass in overall. So impurities in also in the different hemicelluloses and so on.
Yes, and the last thought from my side, to find the right microorganism which can do the work for us. That's a great challenge from my side.
Okay.
That's true. It's not all the other conditions, but of course the microorganisms are also very important in this area of breakage of the polymeric chains of sugars. So if we don't have more comments, I would like again to thank you so much for your contributions. We have today 3 scientists from EPNOE members presenting their works, their results. Thank you so much for sharing with us and all participants of Tecnicelpa your works and your findings, and hope to see you in another opportunity. And thank again Tecnicelpa CRC for this opportunity. It was very interesting for EPNOE to participate in Tecnicelpa, to have this collaboration organizing this event. Thank you so much, and congratulations for this event. Very interesting and very well organized. Thank you so much.
Also, thank you very much, Carmen.
Thank you.
Thank you, and have a nice weekend.
Yeah.
Bye-bye.
Bye bye.
Bye bye.
Bye-bye.